All right, so I want to mention something I just mentioned that. So there's something called a stochastic versus online gradient descent. So in the batch gradient descent, you update your parameters based on calculate the gradient of all samples. So there's one version, something called online gradient descent. So within the online gradient descent, you update the parameters based on individual data, choosing at random. So what I mean here is this. So this is a gradient based on batch gradient descent here. You calculate gradient of the loss function with respect to each individual parameter for each individual sample, and then you average them. And then the alternative fashion is to calculate the loss function based on single loss function based on one samples here. So in that case, your gradient here is not average of m of them here, but just based on randomly pick up the one from the collection of that. And then, so of course, you can see that this gradient here is by no means the same as this batch gradient here. This is the ones we should optimize, right? However, this ones here has some advantage. So one advantage is this is much faster because you are updating parameters, and the moment, after you calculate the gradient of that sample, you update the parameter right away. So, the frequency of updating the parameters is much more frequent than this batch gradient descent methodology. And however, it came as a cost. The cost is this, because this gradient here is not the true gradient here. It's only in the sense is a kind of random samples of the true gradient here. As a result of that, when you update the stochastic gradient descent methodology, your loss function may actually go up and down, up and down, and up and down here. Unlike the original batch gradient descent methodology, your loss function will be monotonically decreasing. Okay, so that's two different versions of that. Monotonically decreasing versus the ones here is trending downwards, but sometimes it may go upwards here. The reason is that because you are doing this stochastically, the sample gradient does not represent the actual gradient of that. So we'll come back to this point here. So although it seems like there's disadvantage of that, but it turns out modern gradient descent methodology are all based on stochastic gradient methodology here. So right now I mentioned that, so this is one example of implementing the online gradient descent methodology here. You can see here in this iteration here, my update here based on one samples. Once I calculate one sample here, update the parameter right away. And in this illustration here is this, right? You start with randomly initialized parameters here. So now you calculate gradient based on one sample here. And suppose based on these samples here, of course, I want to make sure that my line is closer to this ones here. So I'm going to go upwards, here, so that the prediction of this sample is smaller. And that's what I do here. I get this new parameter here. So next, what I'm going to do here, I present it with another samples here. So within these samples, you can see now there's a gap between your observation and prediction here. So what I'm going to do, I'm going to change my parameter theta such that I'm getting closer to this ones here. That's what I do here. I get a new parameter theta here. And so on. You can update a parameter very frequently, right? And soon the data was presented to you, update a parameter. And you can see now, what you can see, there's a path of the solutions go toward optimal solutions, very different from the one you saw previously. The previous, based on batch gradient descent here, it go toward this path of that. But right now, because of this, you're doing online gradient descent here, there's a stochasticity in terms of this gradient direction to calculate. As a result of that, you may go downwards, maybe go upwards in some ways here. So it's not always this kind of monotonically decreasing of the loss function, but instead, in some steps of that, you might increase your loss function of that. But overall, it's trending toward the optimal solutions. That's called online gradient descent here. So the benefit of this, right, is lots of data, and in many cases, the reason is that in many real applications here, you cannot afford to implement the batch gradient descent, because in order to implement batch gradient descent, you have to calculate gradient of all samples of that. And in the case I mentioned, if you have millions of samples, it's just impossible to do that. Just cycle through the entire training data set. It will take you a long time to do that. So if you're using this online gradient descent, it's much better because you have lots of data. you can make more updates per pass. So computation is faster. So disadvantage of this is no longer strictly descent methodology, because your loss function might actually tilt upwards in certain step of iterations of that. And also stop conditions is hard to set. So in the previous way, in the batch gradient descent methodology, usually you stop your algorithm by evaluating that gradient of your batch gradient. If the batch gradient is sufficiently close to 0, and then you stop your algorithm. In this case here, it's harder because your gradient is calculated based on individual samples, and that's not a true gradient. So you cannot stop your algorithm based on this type of gradient here. So you have to use some other methodology, for instance, based on running estimate of the loss function, and then to monitor if the loss function is changing significantly downwards, and you stop that. So however, in general, it's harder to implement the stopping criteria under the online gradient descent methodology. All right, so that's it. So this is kind of different versions for implement this gradient descent methodology, either based on batch gradient or stochastic gradient descent here. In fact, there's a middle ground here. So the ones I mentioned, there are two versions of that. One is calculate gradient based on entire all samples. Then another version is the online gradient. It's calculating sample based on one sample. Of course, you can see that maybe a middle ground is better. You calculate gradient based on a smaller number of samples, but not one, but also is not the entire collection of data sets. You might choose a smaller number of them, maybe use 12 samples to update the gradient. So in that case, you can see that your gradient is more realistic, and there's less stochastic in your implementation there. And in fact, that's how people implement today. So this is something called a mini batch stochastic gradient descent. The mini batch means that you are randomly choosing a smaller number of samples to estimate the gradient, and then you update the parameter based on those estimated gradients. So that's more or less the state-of-art methodology for learning parameters.